Wow, on cue. It's just like class. Everyone gets quiet when So good afternoon, everybody. Welcome. My name's Jamie Phillips, professor and chair of electrical and computer engineering. And it's my honor today to introduce Rachel Davidson as the Donald C. Phillips Professor. I think they picked me to do this just because of the name. We actually have no relation. The professorship honors Donald C. Phillips as an alumnus of the University of Delaware's class of 1948. Through his estate, provided a generous gift to the Department of Civil and Environmental Engineering. And Mr. Phillips earned his bachelor's degree in civil engineering, went on to lead an accomplished career as a construction engineer. And I'm sure he would have been very proud today to see the recent renaming of the department to the Department of Civil Construction and Environmental Engineering. Rachel Davidson is Associate Dean for Academic Affairs for the College of Engineering and a professor in the Department of Civil Construction and Environmental Engineering and a core faculty member in the Disaster Research Center at the University of Delaware. She's also the PI and director of the NSF-funded Coastal Hazards, Equity, Economic Prosperity, and Resilience, or CHEER Hub. So anybody that works on disasters and turns it around to be named CHEER, obviously is an eternal optimist and a very positive thinker. I can clearly remember when I interviewed at the University of Delaware in 2020, and Rachel was in the College Dean's office as a representative to speak with me, and it was obvious to me at the time that she cared deeply about the college community, our students, faculty, and staff, and honestly, that was one of the moments that very much confirmed this is a place I wanted to be. So thank you, Rachel. I've had the privilege of working with Rachel as a department chair and as interim dean, and I've been amazed at her commitment to the college, and honestly, much of what we do with faculty affairs, mentoring, college recognitions and awards, tenure and promotion, and as a result of her leadership, it's a lot of what is really done behind the scenes, out of the limelight, without a lot of the credit that is richly deserved. So I want to take a moment to say that at this point. So in particular, she's been an outstanding leader and champion in the college for our efforts in an area that has been under scrutiny in recent days, but I'm not afraid to say it here, diversity, equity, and inclusion. And as I've heard Rachel refer to it recently, excellence together. So one of our strengths in this college is definitely our community, and Rachel has been at the forefront in fostering an outstanding community here in our college. So I think many of you have worked with Rachel in her administrative role, and today we have the fortune of hearing about Professor Davidson's research scholarship. And in addition to directing the CHEER Hub, I wanted to point out a few other awards and honors. She's a fellow and past president of the Society for Risk Analysis, winner of the ASCE Charles Martin Duke Lifeline Earthquake Engineering Award, and a fellow of the Executive Leadership in Academic Technology and Engineering, or LATE program. So with that, I would like to welcome up Professor Davidson to the podium to present her with this medal for her professorship that she can proudly wear at our academic events. The floor is yours, and I would like to invite you to stay for some questions and answers after the talk, and also reception over in DuPont Hall afterwards.
Thank you, Jamie. Thank you. It's so fun to see all of you here. So I thought I would start today with just a little story. I know some of you have heard this, but it has to do with a student I had when I was just starting out. His name was Hiro. He was from Japan. He was a master's student, very bright. He worked really hard and was quite earnest about his work. And it was getting close to the time he was going to be graduating. He came to my office and he said, "Thank you so much, and I'd like to get you a present to thank you." And I said, "Well, Hero, that's really nice of you, but it's not at all necessary. Don't worry, best of luck to everything. And he said, no, I really want to. I'm going to make you some business cards. And I said, well, Hero, that's very nice of you. I actually already have business cards, but thank you. And he said, no, yours aren't good. I'm going to make you some better ones. And so at this point, I realized I was not going to win this debate. So I said, fine, that would be great. I gave him my office number and so forth. A couple days later, he came back and said, okay, we should take a picture for your business cards. And I was like, Hero, I don't know if I want my picture on the business card. He was like, no, it's much better if you have the picture because then people will remember you. And this is what we do in Japan. And so I was like, okay, fine, we could take a picture. I get up and I'm going to pose for this picture, and he says, at that time in my office, I had a globe that showed where disasters of different types happen, and he said, how about you hold the globe? Because then, everybody will see you'd study disasters. And I was like, I feel like this is gonna look a little silly, but he was very persuasive, so I said, okay, I'll hold the globe. So I took the picture. I thought we were done at that point. He said, okay, last thing we need is your motto. And I was like, Hero, I don't have a motto. He's like, oh, you need a motto. That way people remember you and they'll know. So it was back and forth, and finally I said, look, how about you propose a motto? You suggest something for me, and I'm sure it'll be great. And so he did. And this has been my motto for the last 20 years, freedom from disaster for all people. And it served me really well, and I never got to thank Hero for that. So I'm going to use today as an opportunity. So we're going to talk about disasters. You all know what they are. You read about it in the newspaper and so forth. This is just a good summary to give you an idea of the costs of disasters. This is just for climate and weather-related events, the number of billion-dollar events each year in the US. And you can see there are a lot of them. Last year it was 27. They cost a lot. And they're a very serious problem, and it's growing. But this doesn't really tell you why they're so important. You need to try to understand what happens to a community when there's an earthquake or a hurricane or a wildfire. So these are all photos I took on various post-earthquake reconnaissance trips over the years, and I think start to give you an idea of what it's like when one of these events occurs. And it's one thing to see them on the screen, but when you see it in person and you see a building like this size just crumble, it sticks with you, and it's been very motivational for me. The Haiti earthquake, that's one of my students, and that's basically like their White House in the background. In New Zealand, there was liquefaction that was widespread. That was like a new house in the upper right that just sunk a few feet into the ground when the soil liquefied and lost its bearing strength. There were rock falls and so forth. That's tsunami damage in Japan. But at the end of the day, it's really not even about the building damage, it's about the people. And if you just imagine what it's like for that man who is looking at the remains of his house after Hurricane Helene just last year, and try to imagine what that would be like. That's what motivates me, and I think most of our colleagues, and what we're trying to work on. So what I wanted to do today is try to give you a real brief overview of 3 main areas of work that I've done in this general topic. So hurricane evacuations, infrastructure services, and regional hurricane risk management. So just like a real quick kind of flavor of the kinds of questions we ask, the kind of methods we use to investigate these things. And everything I'm going to talk about is work that was done by a huge group of people, which you'll see. So hurricane evacuation. The main question we've really looked at is, where should official evacuation orders be issued, when, and what type, voluntary or mandatory? So as a hurricane's approaching, like this is Irma approaching southern Florida, a lot is happening. There's a lot of uncertainty about what's going to happen. It's a dynamic situation. people are moving, the forecasts are changing, and there's basically this trade-off. Should they issue evacuation orders sooner? That will give people more time to react, but there's also a lot more uncertainty. And so you might end up with some unnecessary evacuations, which can be expensive and dangerous too. Or if you wait later, you have less uncertainty, but then you have less time to evacuate. So the traditional approach, and what's actually done in practice now, is on the left here. There are hurricane evacuation studies where they basically take information about the hazard, like where we think flooding will occur, the behavior, how we think like people are likely to leave or not. And there's a transportation analysis that says how long do we think it'll take to get the people from these potentially flooded areas out to safety. So that's the clearance time. So they basically look at the clearance time, they look at the forecast time until hazardous conditions and say, okay, we got to make a decision before one is less than the other. So what we try to do is reframe that and instead like really explicitly account for the uncertainty and the dynamic and the interactions among all these decisions in what we call the integrated scenario-based evacuation approach. And that's just one of many acronyms you'll see. So we're trying to mimic the way emergency managers actually make these decisions now. So as a hurricane's approaching, they're kind of repeatedly deciding, should I issue evacuation order now or wait a little longer? Should I issue it now or wait a little longer? And they're kind of stepping through time. And as they do that, they're thinking about, okay, what has the hurricane done until this point? What's the forecast? How much time do we have left? How much time is going to take to evacuate those people? What is everybody else doing? And so we tried to develop a tool that kind of helps integrate all that information. And it turns out it's very well suited to what's called a multi-stage stochastic program. So this is a computational framework. So each of those boxes represents a mathematical model. They're all integrated. And together they provide, at the end, the output is this tree of evacuation recommendations. So like a set of contingency plans. So I'll just step through briefly what each of these are for those of you interested. We start with the modeling the hurricane itself in the top 5 steps, and then we run the evacuation model, which includes an understanding of the behavior of the population and the traffic. So the first step is linking models of the meteorological model that shows how a hurricane's likely to evolve over time. That also produces precipitation forecasts and wind forecasts. The precipitation goes into a hydraulic model. We used CREST. And then they both go into a coastal flooding model. So they're all linked together. And then by perturbing the initial conditions, we generate some uncertainty in how the hurricanes are going to evolve and what the hazard will be. And so we get like an ensemble of scenarios like that. And then we put it all together. We get a total water level and a total wind speed for each scenario at each point in time, like as it's evolving. The next step then is to take that ensemble of scenarios and create what we call the scenario tree. So we said, we've got this set of scenarios that shows like how that hurricane might evolve. And we say, if it evolves the way those red ones do over the next 12 hours, say, starts to go more north, then we think eventually the hurricane will be like one of the red scenarios. So at the end of the day, it'll evolve like one of these scenarios. We don't know which one yet, though. If it starts to go more south, it'll be like one of the blue scenarios. And then in the next time step, if it starts to, like, say it stays south, like the green ones, it'll end up being like scenario 22, 10, 8, or 21. So we're sort of gradually getting more information as the uncertainty is resolved. So the last piece, the evacuation model, includes a lot of study that help understand the behavior of the population, like who we think is going to leave and when, using statistics and machine learning. We've done some work on that. And then a traffic model says if you know the origins and destinations, what's the route that different people are going to take. So if we put all that together, we can get kind of where people are going to be at each time and what's the hazard going to be at that time and overlay them. And so any one location is not inherently safe or dangerous. It's just dangerous if you're there when the flooding happens or when the wind speeds are strong. So it all goes into this multi-stage stochastic program with the objective of trying to minimize a balance of the risk and travel time. And it makes the assumption that we know what's happened until that point, and we know what the possibilities are in the future, but we don't have a crystal ball about what's going to happen. So for an example, this is Hurricane Florence. So if you imagine that it's September 9th, 11 p.m., the hurricane's at that location, you would run the model and you would get a whole tree of recommendations. So instead of just one plan, it's this set of contingency plans. And what it says is basically like at that point, say September 10th, 12 p.m., you shouldn't issue any evacuation orders yet. Basically, you have enough time to wait. But if it starts to go down the red path, then you want to issue evacuation orders in a few places because you're starting to get to a point where either we're sure those places are going to be dangerous or we're going to run out of time. If it went down the blue path, though, you would not issue any orders. If it goes down the blue and then the green, then you would, you wouldn't issue any orders again. So you're sort of trying to adapt as the hurricane evolves. As you can see, so for example, by the end of the day, if it evolves like scenario 9, this blue one, you would have issued evacuation orders in all those places. But if it had ended up like this red one, you would have not issued any. So we're trying to only do them when we have to. And then we can look at the performance of these. So the risk reduction and the travel time kind of go together. Each of these points represents one of the ways the hurricane might evolve. So if it evolves like scenario 9, you're going to end up issuing a lot of orders. You're going to reduce the risk a lot, but you have a lot of travel time, which is sort of the cost. But if it ended up like 10, there's no risk to reduce, but you also haven't made people travel for no reason. If by comparison we just used one plan based on the best forecast, we would have had a lot of people evacuate, and so depending on how it evolved, a lot of that might have been unnecessary. So there's a lot of travel time no matter what. So in the end of the day, like this is a very different approach. And basically some of the benefits of it is we can explicitly trade off risk and time, and we can get this well-hedged, robust solution that's like good no matter how the hurricane ends up evolving. So we're leveraging the value of that increasing information you get as the hurricane moves forward. Okay, so that's hurricane evacuation. It gives you an idea of like one type of work we've done. Second one has to do with infrastructure services. So this is like utilities, basically. Now, ideally, we would not have any infrastructure system service interruptions ever, right? But that's obviously not feasible. So we always have this trade-off again, this familiar theme. You're going to see some themes. We're trading off like how much would it cost to improve the performance versus what are the consequences if we don't. And so because consequences are so important, my colleagues and I, who are here actually, have argued that we need to start thinking about the societal functioning, not just the system functioning. So not just who gets water or power or gas, but what are the daily activities of life that those support. This is going to make it more complicated, so I think we should be clear that there's like a reason to do this. And the reason really is that minimizing the societal objective is that's our true objective. That's what we actually care about. And it's very much related to the system impact, but they're not always the same. So for example, if you have the water is out for 2 hours in the middle of the night in a residential neighborhood, it could be that nobody even notices. But if you have the water out for 2 hours after an earthquake on a windy day, it could be the difference between a small fire and a major conflagration. So they're not always the same. It also gives us more options to reduce the impact. So if we think of this chain of events, kind of, you want to cut it off as early as you can. We can improve the design of the components of the networks or upgrade them. We could develop ways to reroute around damage once we have it. But if we add the societal impact, we can also think about, even if there are outages, how can we manage them to minimize the societal impact? So we end up with these questions. How many people do we think will be affected each year? How likely is it? And what are the interventions we can use? So the standard approach is a Monte Carlo simulation. We simulate, for example, for earthquakes, a ground motion. Then we simulate the damage to the components of the network we're interested in, and then we evaluate the system performance, so who's getting services and who's not. And then the thing is, you have to repeat that a whole bunch of times because there's a lot of variability in it. And if we're worried about earthquakes, we need to repeat it a lot, because in order to get the big ones that we really care about, you have to simulate it for like 100,000 years, because by definition, they don't happen very often. So that's where one of the biggest challenges comes in. So what we've tried to do is make a little bit of a change to the simulation framework. So instead of looping around over and over, we're developing a set of hazard scenarios very carefully. And we're making it a small number and artificially changing the occurrence probability so that that small set matches the hazard of the full set you would get. But it's just a much smaller number, so everything else is much more computationally efficient. And we basically do the same thing then for the damage scenarios, and then model the functioning of the system. And now we've incorporated also the way that utilities restore services, and then translate it also into the societal impact. So step by step again. The hazard scenario, so this is what I mean by finding a small set. So we start by generating a candidate set of earthquake scenarios. So each earthquake scenario is like a fault rupture, a certain magnitude. We generate a whole lot of them. And then we want to select a small number and modify their occurrence probabilities. And so we do that the first step is just based on their contribution. So the ones that aren't very likely or that aren't causing much damage, we can get rid of. And then we have this optimization, which is really the key contribution. By minimizing the difference between the hazard curves we would get with the large number and with the small number, we can actually, and then using that also to determine those probabilities, we can get a really small number of events, and there's almost no difference in the results. We do the same thing for the ground motion maps. So this is just an example for Los Angeles. On the left, we have the ground motion map you would get if you just directly simulated like 300,000 events. And in the middle there is 351. So we get almost the same maps. And then this was for liquefaction for the same thing, which is 350. So now everything is much, much easier, because those later models in the series are very computationally intensive. So we did the same thing in New Zealand, and we went from like 700,000 events to 124. We're only worried about ground motion here, and this is showing the distribution of losses. It was almost the same for both. So it's an enormous computational savings. It just makes everything simpler without much of a trade-off. So the damage scenarios is kind of the same idea. We want to come up with a set of damage scenarios. So each of these would be like one damage scenario, a map showing where there's damages, and each has an occurrence probability that we're going to determine. So we want to do it in such a way that would get the same answer as if we had simulated a lot of them. So it's a similar idea. We actually milked this idea a lot for a lot of different applications. But we just minimized the difference between the curve you would get if you simulated lots of damage scenarios, and then if you simulate just a few, or you take a small subset of that. So here we ended up with like 568. For the system functioning part then, so for each of those 568 damage scenarios, we want to be able to determine who's going to get water service in this case. So one of my recent students developed this model to simulate the system functioning of the water supply system when it's heavily damaged, and then how it's restored over time. So what's challenging here is that when you've got a lot of pipes damaged and a lot of water is leaking, the hydraulics are not the same as normal. So we have to be very careful about that and use what's called a pressure demand analysis instead of the typical one. But then we also tried to tightly couple the hydraulic model and the restoration process so that, so we're capturing the idea that as the operators are restoring services, they're kind of making their decisions based on what's happening at that moment. And finally, the societal impact scenarios. So this part is like all very new. The other stuff was sort of helping around the edges. To try to understand how people respond, we spent a lot of time looking at what we called user adaptation. So when the water goes out or the power goes out, what do? You don't just sit there and cry, right? What do? You adapt in different ways. So we, some of our colleagues at the University of Washington, we looked at Twitter data to see if we could find evidence of people making these adaptations. So here are a couple examples. After Hurricane Maria, people charging their phones either in the car or at a Wendy's, for example. We also looked at a lot of TikTok videos to see if we could find evidence of people making these kinds of adaptations. And this was one example after the Texas winter storms of 2021. And so they had power in this case, but no water. They had snow because it was a winter storm. So she's melting the snow so that you can meet the needs that are the really important needs. You can't maybe do everything, but you can do the ones that you really need to survive, like the coffee. So by looking at these sort of systematically, we found like basically these aren't isolated, clever workarounds that people do. It's actually a very common phenomenon that we saw over and over again, and people do the same kind of things in different types of events in different locations. And implicitly, we're pretty much relying on this. I mean, after the Christchurch earthquake, they were out of water for like a week. And people can only survive without water for a few days. So there was something happening there, right? We're somehow relying on these activities. So we created a typology to start to get a handle on, what are all these adaptations? So we divide them into the ones that work by modifying the supply available. Some work by modifying the demand available. So the infrastructure system focus, so some, like for a generator, will supply electricity for anything you need to do. Some are more use focused. You could get a lantern or a candle. That'll maybe serve your lighting needs, but you can't charge your computer with that. So we kind of tried to understand what the range of them are. We also classified them based on the service they provide. So some are just a partial substitute, some are a complete substitute, what kind of cost is involved in implementing them. So we could kind of start to get a handle on, they're not just millions of different adaptations, there's actually some rhyme or reason to what people are doing. And then we collected survey data, stated preference and revealed preference survey data, and fitted some statistical models, mixed logit models, to try to estimate the probability that a person would do a certain adaptation as a function of how long the outage was and characteristics of those people. And so we're starting to get an idea quantitatively of like how likely it is people will do different kinds of adaptations. And then we also looked at their self-reported unhappiness during these. So we could then put all those pieces together, again, the earthquake occurrence, the damage, the system functioning, and the societal impact, and start to see, like, if an earthquake happened in LA, how many people do we think would be going to hotels? How many people do we think would be trying to do different things and to capture the uncertainty? So these are still pretty early, preliminary. They're not perfect, but we can kind of start to see how we could think about describing the societal impact. Okay, are you still with me? Last example, and you're probably starting to see some similarities in these things. So the way we manage hurricane risk or disaster risk in general in the US is it's a whole system, right? Just like the educational system or the criminal justice system. The current system has limitations, I think, from all stakeholders' point of view. If we just think of Hurricane Ian, which was a couple years ago, this woman, Maribel Gutierrez, lost her home. The house was destroyed. The family had nowhere to go. But from the insurer point of view, the United Property and Casualty went out of business because they had higher than expected losses. And governments also suffered. The Fort Myers had $29 billion they had to spend on recovery that they had to take out of their other normal expenses they were planning on. And this is just one example. It happens over and over again. In general, we see households tend to not strengthen their homes. They tend to not buy enough insurance, and so they don't have adequate resources to recover. Insurers don't like these events at all. They find them very difficult to manage, hard to make a profit, and they worry about going bankrupt. And we're seeing this to a very large extent now, especially in Florida and California, where they're pulling out of the market. And governments also, they end up with these large unplanned expenditures that just wreak havoc. So the thing is, we actually know a lot about disasters. We've been studying this, like the DRC celebrated its 60th anniversary. But somehow we're not seeing a lot of that knowledge in the real world. And I would argue it's partly because in order for that knowledge to be reflected in the real world, just one reason, people have to take some action to do that. And the truth is they just often don't. So the Cheer Hub that Jamie mentioned, we're trying to focus on how can we support policy making or programs that specifically are more likely to actually be implemented. Because A, they align with the way people naturally make decisions. So rather than saying everybody should do this and then thinking like, oh, why are people so silly that they're not strengthening their homes? Let's try to understand how they're making decisions and kind of make a strategy that aligns with that. We want win-win solutions, so we have ideally solutions where all the different stakeholders can end up better off, so there's more likely to be accepted and implemented. And we address some of these competing challenges. So for example, economic prosperity, we don't want, we could say, I know how to reduce hurricane losses. Don't build anywhere near the coast. So I've solved the problem. But I mean, obviously that's not really a tenable solution because people want to build near the coast. There's economic reasons, so forth. So let's find solutions that kind of bake that in from the beginning and realize that that's a competing objective. This is my last computational framework, where each box is a model again, and this has evolved over time, but the green ones are kind of basically estimate losses due to hurricanes to households. We've all focused on housing so far. But what we've done, and that's fairly standard in the field now to have that kind of model from the green boxes. What we've done though is added these boxes at the top that represent the way different stakeholders make decisions, and we've integrated those together. So we have a model that tries to describe how we think the government makes decisions, and we have a model that tries to describe how we think insurers make decisions, and one that shows how households of different types make decisions. And they interact with each other in this game theoretic model. So rather than saying households, you should do this, we're just trying to find the solution, assume they'll behave the way they want to behave, and let's find a solution that works under those circumstances. So what it provides as results is a recommended government policies and a description of how we think the insurers and households will respond. And then importantly, it also shows what the outcomes are for each stakeholder. So we can kind of see, are there going to be winners and losers? So just very quickly to give you an idea of kind of what's in the black box. The loss models are simulations. We come up with a set of 30 years of hurricane scenarios. We have a component-based model of damage to houses, and with and without different kinds of retrofits. The economy is modeled as a computable general equilibrium program to try to show what the effects of capital stock disruption and labor supply disruptions are, and that's broken down by sector of the economy and type of household. For the government, and again, we're going to model the government the way they make decisions, which is different from how other groups do. So the government, we've modeled with a stochastic program, because again, the key issue here is there's a lot of uncertainty about whether hurricanes are going to occur. So they have certain objectives, like maybe they want to minimize the total loss to the whole community. And they have different alternatives available to them. They could issue grants to encourage homeowners to strengthen their homes. They could do property acquisition offers or regulate the insurers. By contrast, the insurers have a different kind of decision. They're also using a stochastic program because there's still uncertainty, but their objective is to minimize or to maximize their expected profit. So they don't care about uninsured losses. They want to maximize their profit. And the things that are in their control are they can decide how to price their insurance and how much they're going to transfer through reinsurance. And they're trying to avoid insolvency. Oh, and then there's insurers interact in a Cournot-Nash game, which is a game theory to capture the fact that it's not a monopoly. And then the households make very different decisions. So they can decide if they're offered a buyout, are they going to accept it or not? Are they going to buy insurance or not? Are they going to strengthen their home? And maybe if they're offered a grant, would they strengthen it? So their decisions are based, like the probability they'll take those decisions based on the terms of the deal. So when the insurer, for example, changes the premium, it changes the chance that the household will buy the insurance. So that's sort of where the interactions come in. So as I said, we end up with kind of the decisions for each type of stakeholder and the outcomes. So just real quick, a case study for the eastern half of North Carolina. If we look at the government decisions, this could show us, for example, as the government invests more money, $1 billion, $2 billion, $3 billion, how much should they spend on the acquisition program versus how much should they spend on retrofit grants? And then what will the expected losses be, or the reduction in expected losses be under those different policies? To look at the households, we can say, so if we start out, imagine that there's no acquisition, there's no retrofits, there's no government investment. For some houses, insurance is affordable, for some it's not. Now if we introduce, say, a $3 billion government investment, some of the households will be acquired, like the ones in red. Some will be retrofitted, the ones in green. And then some won't have either, and the affordability changes because we've changed some of the losses. Now, this is assuming that we're forcing the insurer to keep the price the same. But actually, they're going to want to raise the price if the government makes this investment. So if they do, it changes what the households do. So there's all this interaction. And this is basically what the value of this whole modeling thing is. There are so many interactions within this system among the different players. And we end up sometimes with weird unintended consequences. And we really want to understand how the whole system works in order to come up with the best policies. So the last just example of output, on the left side is the distribution of what the homeowners might pay, the total of what they pay for insurance and any residual loss and so forth. So when there's no investment, the blue line, they're going to be paying a little more. When the government makes an investment, it goes down, and if the government makes the investment and they also force the insurers to not change their price, if it was fixed, then it would go down even more. So we can kind of see, okay, how is this playing out for the government? How is it playing out for the insurers? And then on the right side is an example for the insurers. With those three scenarios, the probability of insolvency changes. So we're trying to find solutions where like everybody is okay, so maybe there won't be as much opposition. And this is work basically that the Cheer Hub is extending and improving this work in a lot of different ways. So that's, I hope, gives you a flavor of the type of work that I've been doing. As I said, this is work over many years, and it's all very interdisciplinary, very collaborative. I'm really afraid I forgot some names, but this was as many as I could remember for the different types of work, and I know some of you guys are here, and so that's actually one of the things I like best about doing this kind of work is that it's so collaborative and there's so many people involved. I also want to make sure before I forget that almost all of this has been funded by the National Science Foundation, so I thank them. So it's sort of become a tradition, I guess, in these talks. People give a little bit of an idea of kind of how they got to this point and say some thank yous. So I thought I could tell you literally how I got to this point. I kind of moved around to different places over the years. But instead, I thought I'd just tell you kind of The truth is I did not plan this at all. When I was a little girl, I didn't dream of studying disasters or any of this. It was more of a like make one decision at a time type thing, and here I ended up. But looking back, it makes a lot of sense to me. When I was a kid, I had a subscription to Games Magazine. I don't know if any of my friends here did. It was basically a puzzle magazine. It was very nerdy, and I loved solving puzzles and stuff like that. I also really wanted to do something where I thought I could, make the world a better place. I could help people, and I loved being a student. And so this was kind of the closest I could find to keep being a student for the rest of my life. And I feel like this career has helped me kind of satisfy all of these parts of me, and so I'm very grateful for it. I also am grateful for all the mentors I've had. People have hosted me on sabbaticals, especially my undergraduate and graduate mentors. But I could call a lot of people mentors, but I thought I should at least think of these people who have played critical roles at critical points in my life, and I thank them. Probably the most important is to thank students and postdocs. I see some of them here because I kind of strongly encourage them to come. But they're the best, like Hero. I love working with them. They're all so different, and they, as most of you know, actually do the bulk of the work that I presented. I also have some really great communities, professional communities that I worked with, and at the moment, I work a lot with the Sim Center, which is a group of universities that does simulation, computational work in disasters. The Cheer Hub you mentioned, we mentioned earlier, is like a fantastic group of people. And I thought I would also call out my Wednesday morning crew. So these guys, we've been meeting at 9 o'clock on Wednesday morning for years. Like a long time, including this morning. And I think that's how we've really been able to integrate the different disciplines. It's 2 economists, a sociologist, and 2 engineers. So really importantly, the Disaster Research Center here at UD is amazing. I am so lucky to be part of it. They're world leaders in disaster studies, and we celebrated our 60th anniversary. I see the 2 co-directors back there. So the DRC is amazing. And in the College of Engineering, as Jamie said, I've had the opportunity to work in the dean's office for a long time, and I've learned so much from that. I'm sorry, it's not a great picture, Wendy, but I gotta call out Wendy, who's here, who actually organized all this, because it's been such a joy to work with her over the last 5 years. My department, who kind of helped raise the kids. I don't know if that's an old throwback picture, but, and Jamie mentioned the DEI work. I know I'm missing people here also, but I know it's under attack now, but I feel very proud of what we've done, and I'm really thankful to all the people who've worked on that. What you're hearing in the news bears very little resemblance to what we've actually done in the college, which has mostly been just about trying to remove barriers so more people could participate in engineering and trying to create a climate where everyone can contribute at their fullest. And that's really all it is. So I'm thankful to all those people who I really love working with. And then outside of work, I'm very blessed to have some really wonderful friends who don't care at all about engineering or academics. And so that helps me kind of turn that off, and they sustain me, and I love them. And last but not least, of course, my family. My parents and brother are here, so thank you for supporting me my whole life, including today, for teaching me to be true to myself, to try to make the world a better place, to have fun while I'm doing it, and Rob and Tess and Eli, I love you guys so much. You make me so happy, and you make me laugh every day, and thank you. And Tess just surprised me and showed up from Virginia this morning, so thank you for coming. And in case you were wondering if I was joking about that story at the beginning, I was not joking. So thank you very much. And I guess we have a reception we can go to, right? Oh, do I have to answer questions first? I'm willing to take any easy questions you have. Or we can chat over food across the... Yes, Michael.
I was just going to ask, over your short career, the impact of social media on sort of disaster response, how has that affected the planning and the way you... So my question was about the impact of social media recently on disaster planning and the response, and how it might get in the way of things because information's coming out and you have plans.
Yeah. So I mean, it's definitely changed the landscape in a lot of ways that we're trying to account for. There's been a lot of work trying to see how social media can be used to better understand the sense making of how, like, in the aftermath of an event, how do people learn what they learn? How do they gather information? We were trying to use it in this way, which was a little bit harder. In evacuations, obviously, it changes things. GPS changes things entirely, the way people decide whether to leave. Now you've got a really precise traffic forecast. Maybe you're more likely to go off the beaten path. Like, it used to be that we would assume people would take the main roads that they normally take when they evacuate. Now you don't have to. You just follow the purple line on Waze, right? So it certainly had a big effect, and I think we're trying to take that into account, and it's always changing. It's also, there's always hope when there's new data that, like, oh, this is going to answer all our questions, and it typically doesn't. There's a lot of challenges with it. Like the smartphone location data we were using to try to understand hurricane evacuation behavior, we thought that it would be like a panacea, and it turned out there was a lot of challenges with it. So, but still helpful. So, yeah. So that's in general though. It's it's a changing environment. So every time you think you've got an answer to something, the context changes. Yeah. Daniel?
So disasters can be a little. Oh, sorry. Disasters can be a little pessimistic. So I wanted to ask, over the course of your career, are there any moments that you've had, like whether it's a technological advancement or really just like a community thing, where you've kind of felt a real burst of optimism or some kind of push where you're like, I can manage this and we are moving in the right place?
That's an interesting question. I hadn't thought of what Jamie said, that we named this cheer. I think, it's a balance. Like, I think we've certainly made huge advances in a lot of ways. I think about like what we know now that compared to what we knew a couple decades ago or 50 years ago. But at the same time, the challenges are growing quickly. So I don't know if we're keeping up. If you looked at that very first plot I showed, the losses are going up. So that can be disheartening sometimes. But there are, if we look at specific examples, there are a lot of really great success stories. And just a couple that come to my head, hurricane forecasting has been a game changer. Just as recently as 1900, when the Galveston hurricane, like, people had no idea a hurricane was coming until it was literally on them. So that's a very different situation than having 3 days of warning to be able to do something. Another example is building codes, which have made an enormous difference in the damage and losses that we see. They only apply typically to new construction, so we still have a big challenge with existing buildings, but there's lots of data to show that building codes have made an enormous impact. And I remember in Christchurch also, they had done a lot of retrofits to the electric power system, and it was very clear that translated into a very much improved performance of the power system. So there's lots of wins like that. So we gotta, focus on those. Jenny?
How willing do you think state and county emergency managers are to do things differently?
That's a good question. I think a lot of them are willing and they're interested in getting help or working together. Like we also have a lot to learn from them. You know, sometimes we sort of conceive of what we think the challenge is, and we find out there's other challenges. With the hurricane evacuation stuff, we had hit a roadblock in actually getting it implemented. I haven't given up entirely yet, but it's been a lot harder than I had hoped. The county and local emergency managers were very interested in it, but we kind of hit some roadblocks in some of the politics higher up. So, yeah, I don't know if that answers, but, you know, I mean, they don't want like every academic is coming up with oh, I've got the answer for you. You know, it takes a while to like earn some trust and develop a relationship, but everybody wants the same things, I think.
Hey, Rachel. So I'm not sure if you know, but we were in Christchurch 2 weeks before the earthquake hit. And so you talked about two extremes, the hurricanes, where you can actually kind of maybe predict where it's going to hit, and the earthquake, which arrives unannounced. What about intermediate type disasters like wildfires, in which, you know, I was thinking Pacific Palisades is a great example of unpredictability there.
Yeah, so I've been really interested in kind of cutting across different disaster types. So obviously, like if you're a meteorologist, you just do climate-related things. It's very different than an earthquake, which would be a geological phenomenon. But for someone interested in the risk like me, we can kind of go back and forth, and it's always very interesting, I think, to take lessons from one hazard and try to adapt them or translate them to other ones. So wildfire obviously has become much more of a front and center concern. And I think there's some things that are similar, like, you know, we evacuate from wildfires. So it's similar to hurricanes, but it's also different. It's also, you know, the protecting buildings. There are certain things we can do, but there's different challenges there also. So, yeah, I don't think we can do the same kind of scenario-based approach for wildfires yet that we talked about here. They're very difficult to predict where they're going exactly. One of the main ways they spread, so I actually did a lot of work on post-earthquake fires at one point, and one of the main ways they spread is these embers can fly like a kilometer. And so you just get this spotty spreading that's very hard to predict. And it makes a huge difference whether it's windy or not. So, you know, some of it's also just getting bad luck. But I suspect there will be a lot more research in that area in the coming years, and so we'll probably hopefully get better at managing the wildfires. Yeah.
We can continue
Yeah.
conversations over refreshments.
Thank you. Okay. Thanks for coming.